Hello, everyone. My name is Bhargavi Parthasarathy. I am a math PhD student at Syracuse University, and my advisor is Graham Lusky. I like thinking about maximal Cohn-Macaulay modules. Before I tell you more about them, as an algebraist, consider a polynomial ring. And think about n by n matrices where the elements or the entries of the matrices are from your polynomial ring. If you can find two matrices such that when you multiply them, you get the polynomial, a polynomial, times the identity matrix of the same size. These kind of matrices are called matrix factorizations. These pairs are called matrix factorizations for this particular polynomial. And well, as a commutative algebraist, I like these because if you think about the polynomial ring quotiented out by this polynomial, the co-kernels of these matrix factorizations correspond to maximal Cohn-Macaulay modules, which is what I like studying. Now, a common question a lot people like asking is if you wanted to write this, is it finite? And we don't know when it's finite. But in the cases where it's not finite, you want to think about whether is it countable? If not, can you parameterize it? A particular example is in 2002, Laza, Feister, and Popescu gave a list of these matrix factorizations for a particular elliptic curve, which is x cubed plus y cubed plus z cubed. And in particular, for rank 1 MCM modules, these matrices could be either 1 generated, 2 generated, or 3. So these are the sizes of the matrices. And for each size, these matrix factorizations correspond to points on this elliptic curve. And well, the thing that I was studying was if you thought about homomorphisms of these modules, MCM modules, so maximal Cohn-Macaulay modules. For rank 1 MCM modules, these maps will also be rank 1, and they will also be MCM. So these modules, the HOM modules, will also be on this list. Well, that was not what my research was about. That's obvious. But what I did was, if you started with these two different points, can you somehow use the natural group law on the elliptic curve get this corresponding HOM object? And turns out you can. And that's what my research has been about. Future direction that I've been considering is, can I extend this to all elliptic curves, and what would that look like? Thank you.